Okay. Now we're live. All right, so today we're going to continue some gas calculations. We're going to talk about Dalton's law, gas density, and finding molar mass of a gas, which are all based on the ideal gas law. So let's refresh our memory. What is the ideal gas law? It is what formula? PV equals nRT, right. All right, so let's talk about Dalton's law first. Dalton's law says that the total pressure of a mixture of gases is the sum of the pressures of all the individual gases, right? So if I've got a mixture that contains argon and helium and nitrogen, right? Then the total pressure would be the pressure of the argon plus the pressure of the helium plus the pressure of the nitrogen, right? That's what Dalton's law says. So mathematically, right, the total pressure is equal to the pressure of gas number 1 plus gas number 2 plus gas number 3, et cetera, right? This is the total pressure, and then these are the individual gas pressures. Make sense? That's all Dalton's law says. Not really all that complicated, right? Of course, we're going to make it more interesting, but let's just start simple. All right, so partial pressure is the pressure exerted by a gas that is a component of a mixture, right? So if I said in my previous example, nitrogen, argon, and helium, right? So each one of those would be a component. Each one of those would exert a partial pressure. Now we are assuming that there are no interactions between the gas particles, right? Because if those particles are reacting, those particles are exerting strong intermolecular forces, etc., right? That would definitely mess this up. So we're pretending, we're assuming there are no reactions occurring, there's no interactions taking place. Okay, now, here's the ideal gas law, right? PV equals nRT. Let's rearrange it for P. How do you get P by itself? Well, if you get P by itself, you just divide both sides by V, right? To get P by itself. P would be nRT over V, right? Do we agree? All right, so we're going to substitute nRT over V in for P, okay? So for gas number 1, number of moles times R, which is constant, times the temperature divided by volume for gas number 1, plus number of moles times R times T divided by volume for gas number 2, plus number of moles times R times T times volume divided by volume for gas number 3, et cetera, et cetera, et cetera. All right, so we're just rearranging the ideal gas law. We're substituting that into our P total. Now we're going to factor out this. We're going to factor out, because notice RT over V is appearing in all of these. RT over V, RT over V, RT over V. So if we factor that out, just like in math, all right, we factor out that quantity. Then we can say P total is N total times RT over V, right? Number of moles, total number of moles, times RT over V. I'm just showing you where it came from right here, right? These are the two Dalton's law equations that we're going to be using today. If all you know are pressures, then you just use that top one. That's the easy way. But if I give you more information, because I'm always going to give you more information, right? I don't like leaving you in the dark. I want to give you lots of information, right? Then you would use the second one. I'm not going to make you derive this on a test. Okay, I just want you to understand where things come from. I personally do a better job with formulas if I see where they come from, as opposed to me just saying, here, memorize this. Right? For me personally, I like to know where stuff comes from. So let's do this one together. Mixtures of helium and oxygen are used in scuba diving. Anyone know what scuba stands for? Does anyone remember? Anyone ever used scuba? Self-contained underwater breathing apparatus. Mixtures of helium and oxygen are used. 46 liters of helium at 25 degrees Celsius and 1 atmosphere pressure. 12 liters of oxygen at 25 degrees Celsius and 1 atmosphere pressure are pumped into a 5-liter tank. Calculate the total pressure in this tank at 25 degrees Celsius. Now here's something I recommend that you do. This is something that I would do as a, just to help me keep it organized. I would make myself kind of like a little graph, some sort of little schematic. Because boy, you got a lot of numbers going on here, right? That wouldn't help. I'm just trying to make it go up there. There we go. Now we can read it a little better. I don't know, maybe that made it worse. Who cares? So we've got a lot of numbers here, right? Yeah, I guess that did make it worse. We've got helium and oxygen. So what I would do is I would just kind of make myself a graph, like a little chart here. Okay, this is my helium, and it's 46 liters, and it's at 25 degrees Celsius, and it's at 1 atmosphere pressure. Okay, and then this is obviously not going to be to scale. There's 12 liters. Obviously 12 liters will be a lot smaller than 46, but who cares? This is O2, 12 liters, 25 degrees Celsius, and 1.0 atmosphere pressures as well. Now here's nice and convenient, because they're at the same temperature and they're at the same pressure. Would I do that in the future though? Have one be at one temperature and one be at a different pressure? You bet, right? So listing out all your information is a good thing. And then we make some sort of way of combining them into a 5-liter tank. So here's the mixture. This is my mixture. It's 5 liters, and it's also at 25 degrees Celsius. Well, that's very convenient, right? What if this one was at 50, this one was at 30, this one was at 15, right? I could be at a whole bunch of different temperatures. So if you make yourself some sort of little schematic, the more numbers I throw at you, and you know me, right? I will, the easier it is to keep everything organized, right? Because now you can calculate number of moles. Now you can calculate number of moles here. Now you can calculate number of moles here. And then when you add those two together, that'll give you N total, right? And you know the temperature and you know the volume. Does this make sense? So that's why we list out all our information. So what are we going to do? We're going to have to use the ideal gas law here to get number of moles. We're going to have to use the ideal gas law here to get number of moles. Then we're going to add those together, and that'll be N total, right? Because if P total is N total times RT over V, right? We know the T, we know the V, we know N total by adding those two together. Does everyone see the big picture here, what we're going to be doing? Okay, that's why I say make yourself some lists, because right now everything's at 25 degrees Celsius, nice and convenient. It's not going to stay that way because you guys know me. So let's go through how we do this. Just a reminder, right, we're using the ideal gas law, which is PV equals nRT. Yes? So we need to figure out number of moles of each gas, right? So if PV equals nRT, to get N by itself, we just divide both sides by RT, right? So I'm just rearranging the ideal gas law here. That's all I did, right? PV is equal to nRT, then N is PV over RT. I just rearranged that. And now I plugged in straight from my little schematic that I just drew. So I've got 1.9 moles of helium, and I've got 0.49 moles of oxygen. Does everyone see how I did this? Because in my little graph that I just drew, my little flow chart, whatever you want to call it, right, I said to myself, okay, I need to calculate number of moles of each one of these. So I just used the ideal gas law to get number of moles of each one of these. Now I can add those together to get total pressure, right? P total is equal to N total times RT over V. So N total, add these two together, and then multiply by R, temperature in Kelvin, over V. And I get 11.7 atmospheres. Does everyone see how we did this? So you're going to have a lot of numbers in these problems, right? In our word problem back here, right, we had a whole bunch of numbers about different gases, and then the tank itself was at unique conditions. Well, actually, in that one it wasn't, but in the future, expect it to be. Right, so just make yourself a little schematic, or list it out, or do something, right? Because especially if you're a visually oriented person, having a way to keep all that information organized is really crucial, because then you won't be plugging in the wrong volume in the wrong place or the wrong temperature in the wrong place. Right? If you just keep everything nice and neat and organized, that's really the key here, because the math isn't difficult. What's difficult is just staying organized. Makes sense? Ready to try one for yourself? Okay, try this one. 22 liters of argon gas at 33 degrees Celsius under 1.4 atmospheres pressure is mixed with 17 liters Krypton gas, 38 degrees Celsius under 1.9 atmospheres pressure. Mixture is pumped into a 10-liter tank at 28 degrees Celsius. What's the total pressure in the tank? I'll pause the recording, give you some time to think about this one. Let's look at this one. So we've got a lot more numbers to deal with this time. And this is, again, why I recommend making yourself a chart of some sort so that you can keep everything organized. And so here we go. Let's see, we've got, oh, that's a sad looking triangle. We got argon, 22 liters, 33 degrees Celsius, and 1.4 atmospheres pressure. And we've got Krypton, and it's 17 liters, and it's 38 degrees Celsius, and it's at 1.9 atmospheres pressure. And then we're going to mix these into a tank. This is our mix. The mixture is 10 liters and 28 degrees Celsius. So like I said, I'm going to not keep everybody at the same temperature. I'm going to keep everybody at different pressures, right? Because I want to make sure you're paying attention. So we can calculate number of moles here, number of moles of argon. Then we can calculate number of moles of Krypton. And then we can calculate P total is equal to N total times RT over V. And again, this is of the mixture. Right, so that's using the temperature and the volume of the mixture, not any of these volumes up here. Right, so if you want to write mix, just to keep it straight. Okay, so if you make yourself some sort of little schematic, that really helps with the organizing of the data, and that reduces the probability of silly, careless errors. So we need to calculate number of moles of each one. I got 1.22 moles for argon, and 1.27 moles for Krypton. And then total pressure, I got 6.2 atmospheres. Do we agree? Use the ideal gas law up here to get number of moles of argon. Use the ideal gas law down here to get number of moles of Krypton, and then plugged it into my Dalton's law, modified Dalton's law expression. We good on this one? Okay. Now, we can also use Dalton's law in terms of atmospheric pressure, right? Because right now we're breathing a mixture of gases, yes? The atmospheric pressure we're experiencing is the result of that air pressing down on us, right? So all the mixture, all the gases in the air we're breathing will add up to the atmospheric pressure, right? That's something we can look up. So let's decide which formula we need to use here. Air, which is a mixture, right, contains oxygen, nitrogen, carbon dioxide, and other stuff. We're just going to lump it all together, other stuff. What's the partial pressure of oxygen at 101.3 kilopascals, total pressure, with the partial pressures of nitrogen, carbon dioxide, and all the other gases are 79.04 and 0.94. Do I need to use the complicated, quote-unquote, method here? Or is this just subtraction? Remember, there are two variations on Dalton's law. P total is equal to N total times RT over V. And P total is equal to P1 plus P2 plus P3 plus P4 plus P5, right? Do I have any volumes? Do I have any pressures? No, right? So can I use the second one even if I wanted to? No, because I don't know the volume of the air we're breathing, right? All I know is that it's a mixture. And I know the total pressure, and I know the individual partial pressures of a lot of them. Do I need to worry about converting this to atmospheres, or can I leave it in kilopascals? You can leave it. You can just totally leave it. Right? So this one is the simple method, right? If the total atmospheric pressure is the pressure of nitrogen plus the pressure of oxygen plus the pressure of carbon dioxide plus the pressure of everybody else, I just plug in my values from the problem and solve for O2 by subtraction. So here, you don't have to go drawing out schematics because you don't have much to do, right? So don't overcomplicate it. Sometimes it's a really easy calculation. Okay, so that's why I show you this one after the complicated one, right? Because a lot of times I might give you a really easy one, and you try to make it a lot harder than it is, okay? Let's talk about mole fraction. So we don't use molarity when we're talking about concentration in gases. That just doesn't make sense. This isn't a solution, right? It's not like you have something dissolved in something else. But we can talk about gas concentration in terms of proportion. So we're using the Greek letter chi, which we've actually used already once before this semester. Use it to represent electronegativity. And there are two ways that we can calculate mole fraction. They're both ridiculously easy. I think everyone in this room could do when awakened from a deep sleep. First method is using number of moles. So number of moles of the gas you're interested in divided by the total number of moles in the mixture. All right, so if I said, what's the mole fraction of, I don't know, Cl2? If you've got 5 moles of Cl2, and a total number of moles of 25. I think everybody could do that, right? So we can do it using number of moles. We can also calculate it using partial pressures. So if you know the partial pressure of your gas, and you know the total pressure of the mixture, you can calculate mole fraction this way. So either way, using moles or using partial pressures will work. And notice, it's gonna come out unitless. Right, because if you have atmospheres over atmospheres, atmospheres and atmospheres will cancel. If you have moles over moles, they'll cancel. So your mole fraction will be unitless. Easy enough, right? Okay, so let's just do one for practice. I'm not even going to pause the recording. You could probably just do this in your head. Partial pressure of oxygen is 156 torr. Total pressure, 743 torr. What mole fraction of oxygen? Is this a complicated calculation? No, it's just division, right? Notice there are no units because torr cancel. Do you need to convert to atmospheres? I mean, you could, but you don't need to. Unless I specifically said, make sure all your pressures are in atmospheres in the problem. Everybody good? All right, what about this one? If the mole fraction of neon is 0.781 and the total pressure is 298, what is the partial pressure of neon? So if mole fraction is 0.78, total pressure is 298, what's partial pressure of neon? Do we have to do some nasty math here? Now, this is really easy, but it's different, right? Because this time we're saying x over 298 is equal to 0.78, right? So we just have to do a little tiny bit of algebra, right? So 233. Does that make sense? That's reasonable. Everybody good on how to do this mole fraction? Your new homework that's going up tonight will have mole fraction questions on it, I'm almost certain. Okay, let's talk about in terms of practicality. If you're doing an experiment, you want to capture a gas. Okay, capturing gases is difficult, right? That's something that's hard to do. And so let's pretend you've got an experiment that you're doing here, and you're producing a gas that doesn't dissolve in water, right? That's the key. Because if your gas dissolves in water, well, then you're sunk. But let's just pretend that you've got a gas that doesn't dissolve in water, it's insoluble in water. And so you're trying to capture it. So you're doing some sort of decomposition reaction here, or whatever. And you're generating a gas. You want to capture it. Well, it's hard to do because if you just kind of leave tubing up here, you're building up pressure, you got places where it can leak. There's a lot that could go wrong. But if you have some tubing, force it to go down the tube and into the water, and then you can collect it up here, right? Then you can measure its volume. This is usually an inverted graduated cylinder. You're actually going to do an experiment like that this week or next week. You're going to be capturing the gas, and you're going to be reading the volume. This is just going to be an inverted graduated cylinder, so you can read the volume as it expands. But you do run into a problem, right? Because if you're bubbling your gas up, you're going to have the gas that you're capturing, but you're also going to have a small amount of water vapor in there too, right? Because this is liquid water, right? There is going to be some vaporization taking place. And so you're going to have to factor out that water vapor. Does everyone see why we have a slight issue we have to work around here, right? Because this water is vaporizing. There's nothing you're going to do to stop it, right? Unless you're at some extremely low temperature, and then that'll make this part difficult because then you wouldn't bubble it through the water. You'd be trying to bubble through ice, and that would be hard, right? So we're going to have to subtract out the total atmospheric pressure minus the pressure of the water, which we can obtain pretty easily too. So here's an example. 1.3 liters of oxygen gas at 20 degrees Celsius is collected over water. And make sure that when you see this in the problem, if the problem explicitly states it's being collected over water, that's important. That's an important detail for us. The vapor pressure of the water is 15 torr, and the total atmospheric pressure is 49 torr. So I want to know what's the vapor pressure of the oxygen gas, and then how many moles of oxygen gas did you collect? Your experiment that you're doing, I actually want to say it's this week. No, it's not this week. This week we're doing Guess's Law. It'll be next 2 weeks from now. Yep. 2 weeks from now. We'll be collecting gas over water. All right, so because this is being collected over water, we have an extra step that we need to take into consideration, right? Because we have to subtract out the water vapor, right? So the vapor pressure of the O2, we're just going to use Dalton's law, right? Total pressure is equal pressure of the oxygen gas that we're interested in plus the vapor pressure of the water, which we don't want. Right, so we're just going to subtract. So the pressure of the oxygen is 34. No temperature, or volume, or anything needed there. Does everyone see how we did this? So we just subtracted. Now the problem asks how many moles of O2? Well, now there's only one way we can get number of moles. And what would that require us to do? VV equals nRT, right? So that's the only way we can do this is by the ideal gas law. So we're listing our variables. Can I keep my pressure in torr and plug it into the ideal gas law? Can I keep it in torr? No, I can't, right? Because R has units of liter atmosphere. If I've got this in torr, atmosphere and torr don't cancel each other out. So the handout that I gave you last week has all your conversions. 1 torr, there are 760 torr per atmosphere. Right? So you need to convert torr to atmosphere. Can I leave this in Celsius? Can I leave Celsius as that? Nope, got to convert to Kelvin. Am I okay with that volume? Volume in liters is fine, yes. And R is a constant. So I've got to first convert torr to atmospheres, 760 torr per atmosphere. Now I can plug it into the ideal gas law, right? If PV is equal to nRT, how do I get N by itself? I just divide both sides by RT. Or you could plug directly in, just dump it all in there, right, and do your algebra. You get the same answer either way. Make sense? Atmospheres cancel, liters cancel, Kelvin cancels. I'm left with 1 over moles, which would then just be moles. as my unit. Ready to try one? 14 liters carbon dioxide at 30 degrees Celsius is collected over water. Boy, that's a big container. The vapor pressure of the water is 165 torr. Total atmospheric pressure is 878 torr. I want to know what's the partial pressure of the CO2, and I want to know what mass of CO2 you have. Think about how you would get mass. So, because this is being collected over water, that does make an extra step for us, right? But it's just one little tiny step. It's not a big intrusive calculation. It's literally just what? We have to subtract. That's it. That's easy. Right? So to get the partial pressure of the CO2, that's just subtraction. That's easy enough. Can I leave torr as my unit of pressure? No. Got to convert it to atmospheres. There's 760 torr in 1 atmosphere. Right? So I convert it to atmospheres. And now I plug into PV equals nRT. And that gives me moles. But the problem asked what mass. So I had to take it a step further. Right? I have to convert moles to grams. Molar mass is 44 grams per mole. Final answer, 23 grams. Do we agree on this one? All right, let's talk about gas density. Density of a gas. Not all gases have the same density, right? I mean, think back to last week. I showed you the picture of the 2 balloons. One was floating, one was not, right? That's gas density. And so we know what density is. I mean, we talked about density on the first day of class. Density is mass over volume, right? And that's going to work for any density of anything. Density of liquid, density of solid, density of gas. Doesn't matter, right? Density of whatever, density of you is mass over volume, okay? So we can do gas density. We're just going to have some more fun getting there, right? Because we can get moles from the ideal gas law, which we can then convert to grams. So that gives us the mass, right? And then divide by volume, we got the density. So we're going to use the ideal gas law again, yay, because a gas at a lower temperature is going to have a different density than a gas at a higher temperature, right? We've got to factor in temperature, and we got to factor in the volume, right? The density of a gas in a very, very small container is going to be different than the density of gas in a very large container. So that's why we're going to have to use the ideal gas law. To get mass, we have to convert to grams, and then we can divide by volume. So let's do this one together. A 1.5 atmosphere, 27 degrees Celsius, the volume of argon in a container is 4.9 liters. What's the density of this gas? I'd tell you a good joke, but all the good ones are gone. All right, so my bad joke aside, we have to calculate density here, right? Because density is going to vary. If we were in a 49 liter vessel, right, the density would be different because gases expand. So because gases are so variable, we have to figure out the number of moles based on these specific conditions. All right, so first thing we have to do is we have to use the ideal gas law. I told you the ideal gas law is the only one we care about, right? Charles' law, Boyle's law, they're great, but we don't need them here. We want to calculate number of moles, right? If PV is equal to nRT, how do I get n by itself? Divide both sides by RT, right? N is PV over RT. Of course, you could just plug directly in here and then do your arithmetic. You get the same answer either way. So that gives us number of moles, but density is not moles per liter, right? It's grams per liter. It's mass over volume. So I've got to convert moles to grams. Molar mass of argon, 39.95. Oh, excuse me. Now we can divide for density. Density is mass over volume. Volume is 4.9 liters. Mass we just calculated. So my units here are going to be grams per liter. So ideal gas law is going to be a part of pretty much every calculation you're doing during the gas stuff, right? Because gases are so variable. So we have to take into consideration things like temperature and volume. Does everyone see how we did this? Calculating the density of the gas, right? And gases will separate based on their densities. So you do this one. What's the density of 8.1 liters of chlorine gas at 36 degrees Celsius under 2.5 atmospheres pressure? All right, let's go over this one. So this is chlorine gas, which is diatomic. That would make a difference here, right? If you factor in molar mass of 35.45 versus doubling that, that will make a difference, right? So first of all, we need to calculate number of moles for the ideal gas law. I got 0.799. If you rounded yours ever so slightly, probably isn't going to make a difference. Then we're going to convert to grams and then divide by the volume. 7 grams per liter is what I got. Did you? 2 sig figs? If you made a mistake, you see we made it? All right, let's skip that one actually, because I've got a bad science clip I'm going to show you after the recording. It has to do with gas density. And let's very quickly talk about finding molar mass of a gas, okay? Because we can do an experiment to determine molar mass of a gas. That's actually not a very difficult experiment. We're going to derive the formula. Again, I'm not going to make you derive the formula on a test. Just for your own mathematical curiosity, I like to show you where formulas come from. If the derivation, if it isn't too nasty. The derivation is nasty, then I won't show it to you. But it's an easy calculation, right? Because in the ideal gas law, N is number of moles, right? And so that's mass over molar mass, grams per mole, right? And so if we substitute that into the ideal gas law and rearrange for pressure, P is equal to nRT over V. So if we substitute N as mass over molar mass, and since density is mass over volume, right? Mass over volume, this little piece goes away. That's density. So we can say P is equal to dRT over molar mass. And then if we rearrange this for molar mass, we can get molar mass is equal to dRT over P. See? Not a hard calculation, not a hard derivation. That's the formula for molar mass. Density times R times temperature divided by pressure. Now, what if you don't know the density? Well, you'd have to calculate the density first and then plug that in here, right? Because I'm just mean. I could give you the density because I'm nice, but I could be feeling mean and make you calculate it. So molar mass is equal to dRT over P. D is density, which you may or may not have to calculate depending on how nice I'm feeling. R is gas constant, T is the Kelvin temperature, and P is atmospheric pressure. So here's an easy one. I say it's easy because I'm giving you the density. The density of gas was measured at 1.5 atmospheres, 27 degrees Celsius, and found to be 1.95 grams per liter. What's the molar mass of this gas? Well, I was really nice, right? Because I told you the density. That means you don't have to calculate it. That means you can plug directly into dRT over P, and you're off to the races. Right? So dRT over P, dRT over P. Molar mass here will be 32 grams per mole, right? Because, let's see, atmospheres cancels, kelvins cancels, liters cancels. That leaves you with grams over moles. So this one's easy because I gave you the density. That was very sweet of me. How nice. Of course, if I don't give you the density because I'm feeling devious and mean, right, which is a very real possibility, then you calculate the density using the procedure I just showed you and then plug that in. So this one's a little more involved. You do an experiment to calculate the molar mass of hydrogen gas. And here are your data. You get a pressure of 1.2 atmospheres, temperature 25 degrees Celsius, and the volume is 3.8 liters. And I want to know, what's your experimental value for molar mass? Was it a good day in the lab or was it a bad day in the lab? All right, so what are we going to need? We're going to need to calculate density first, right? dRT over P. So how are we going to calculate density? From pressure, volume, and temperature. Right, we're going to need mass divided by volume. But then how am I going to get mass? calculate moles, which I then convert to grams, right? So I am going to use the real molar mass here. I have to. There's the only way I can do that. Random number of moles there. All right, so the first thing I'm going to do is I'm going to solve for number of moles using the ideal gas law. Then I'm going to convert grams to moles. Like I said, I have to use the real molar mass here. That's the only way I can do this. Otherwise, I'm stuck. And then I'm going to divide by the volume. And now I can plug it into dRT over P to get molar mass, 2.02. I came up with 2.02. The actual molar mass is 2.016. So is that a good day in the lab? Yeah. Pat yourself on the back. All right, good work. This is the last problem you're going to do today. And then I'm going to show you a little video clip. Density of ethene, C2H4, was measured at 2.9 atmospheres, 24 degrees Celsius, found to be 3.34 grams per liter. What's the molar mass under these conditions? Oh wait, no, there might be two more. Because I was just thinking, I think I give you the density and then I don't give you the density. We can make it work. Video clip is very, very short. So, is this calculation a complicated one? No, this one's easy, right? Because I gave you the density. So all I do is plug it in, dRT over P. 28 grams per mole, which is the actual molar mass. So, good job. Here's a more involved one. You set out to determine the molar mass of Krypton. Here are your data. Pressure is 4.6 atmospheres, temperature is 20, volume is 0.92. What's the molar mass of Krypton? And then, was this a good day in the lab? Or do you have room for improvement? I'm going to pause it for this one. All right, let's look at the solution to this one. So, I didn't give you density this time, right? Which means you're going to have to first calculate density, and then you can solve for the molar mass, right? So density is mass over volume, so I have to first calculate number of moles using these data and the ideal gas law. Number of moles, convert to grams, divided by this volume. That'll give density, and then I can plug it in. So number of moles, I got 0.176. When I convert moles to grams, I got 14.7 grams. And then when I divide by the volume from the problem, I got 15.97 grams per liter. And now I can solve for molar mass, dRT over P, 83.5, which is pretty close to the real molar mass of 83.8. So if you got that in the lab, 83.5, molar mass is actually 83.8. That's a good day in the lab. That's a woohoo, gold star. So like I said, these calculations aren't difficult. You just have to watch. And the ideal gas law is going to be involved in every single one of them. Okay? There's always going to be the ideal gas law, unless you're doing the most basic Dalton's law subtraction / adding problem. All right, so where are we going from here? On Wednesday, because we can calculate number of moles, that means we can do stoichiometry. So everybody's favorite. So that's where we will be going on Wednesday in our next lecture. All right.